Hello everyone, my name is YADATA. Today I'm going to explain my digital assignment 1 and digital assignment 2 of computer organization architecture. I'm gonna share my screen. This is my digital assignment 1. Uh, Analysis of microprocessment element and microprocessor or IP core. IC I selected ARM Cortex M1 according to the plan you listed for us. So many Cortex M is there. Some student chose M7, M0, M5, and M3. So I chose M1 for myself. Based on this ARM Cortex M1, I did the following diagram and brief explanation as follows. A small microprocessor designed optimized for FPGA designed and provides uh, tightly coupled memory implementation using memory blocks, same instruction as the Cortex M0. Instruction is the same with M0. This M1 Cortex is question number 1 said draw the clear block diagram of microprocessor and the microcontroller IP core selected. My IP core selected is ARM Cortex M1. So this is the diagram I drawn. Uh, the online I used it to draw this online tool diagram. Uh, there are so many different tools to use for this drawing purpose. So for this digital DA1, I use this and in downward I explain this number 1, number 2 up to number 3 for the indication of NVIC interrupt interface. In this the first box, this number 2 represent external HV live interference interface, and this number 3 SW or GTEG interface description as follows. The core has the following main features: three-stage pipeline, multiply cycles, 3 cycles for a normal multiplier, 3 cycles for a small multiplier, time state, handler, and the thread modes, and registers. The processor contains 13 general purpose 32-bit registers, link registers, program counter, program status register, 2 banked SCP registers. Without the OS extension option, there is only one SCP register present. And question, these all are sub diagram. This is debug. The 2 configuration for debug. The full debug configuration has 4 breakpoint comparators and 2 watchpoint comparators. The main block of the processor without the debugs are core memory interface, NVIC, bus master, HV, TPBB. This is also the diagram for debug. Description: core memory interface, core access to tightly coupled memory. TSME is made exclusively through dedicated core memory interface. The core memory interface comprises as follows. Question number 2, provide the instruction set of the microprocessing element, microprocessor or microcontroller IP core with clock cycle required, machine cycle required, memory required, flag affected, type of instruction based on addressing mode, operation, extra. The Cortex M1 processor are based on the ARM V6M architecture, which has a small instruction set of just 56 instructions, and most of them are 16 bits. However, the registers in the processor and the data being operated on these are still 32 bits. For most simple input-output control tasks, general data processing, this small instruction set is sufficient. Instruction sets are thumb1, most of thumb2, some 32-bit hardware integers, 1 to 32 interrupt. ARM instructions can be made to execute conditionally by post-fixing them. These syntax are like as follow, like this one, and this table are a syntax and explanation, condition, symbol, and flag. Equal is equal to. N is not equal to this abbreviation. This is the symbol. This is a description for the how they called. This is the flag set and the processor models. User used for executing most application program. FIQ used for handling fast interrupt. IRQ used for general purpose interrupt handling. Supervisor are a protected mode for the operating system. Undefined entered upon undefined instruction exceptions. Abort entered data after prefetch aborts. Monitor a secure mode for trust zone. Processing operating status. The Cortex M1 processor has two operating states, thumb state and the debug state. Thumb state, this is a normal execution running the set of 16 bits. Debug state is the state when halting debug processing operating modes. The thread mode entered on a reset and can be re-entered as the result of exception return. And also this ARM Cortex M1 processor support 10 addressing mode, immediate offset, register, scaled register offset, register offset, this also run, and etc. Question number 3, explain microprocessing element with diagram. This is the architecture I drew for the question number 3. The Cortex M1 processor implements a subset of thumb2 architecture called ARM V6M. This includes all of the 16-bit thumb2 instructions and some more of 32-bit instructions. The ARM architecture, arithmetic logic unit, boot multiplier, barrel shifter, control unit, register file, and the deep explanation for all of it. For example, arithmetic logic unit represented by ALU. The ALU has two 32-bit inputs. The primary comes from the register file. The other comes from the shifter. Status register flag modified by ALU output. The V bits output goes to the V flag, as well as the count goes to the C flag. Whereas for most significant bits really represents the S flag. ALU operation is done by NOR to get the Z flag. Boot multiplier factor. The multiplier factor has three 32-bit inputs and the input returned from the register file. The multiplier output is barely 32 least significant bits of merchandise. Boot algorithm and also barrel shifter control unit. All of it explained as the above. Question number 4, correlate the microprocessing element architecture with architecture discussed in the module 1. This is the diagram, architectural diagram I drawn for this one. This architecture is a AT51 microcontroller. This diagram is architecture for ARM Cortex M1. The above is for AT55 microcontroller. This for ARM, for IC which I was chosen. Question number 5, elaborate register organization of microprocessing element. The microprocessing has the following 32-bit registers, 13 general purpose registers, R0 up to R12, stack pointer, R13, link register, program counter, program status. These all 13s are in this table below. Low register R0 up to R7, high register from R8 to R12, stack pointer processor, stack pointer main R13, program status register, XPSR, general purpose registers. The general purpose registers R0 up to R12 have no architectural specific uses. Low registers are accessible by all instructions that specify general purpose registers. And the special purpose program status register, processor status as the system level is broken into 3 categories. Can be accessed as individual register, combination of any 2 of the 3, or a combination of all 3 using MRS and MSCR instructions. Question number 6, explain the type of algorithm used by signed or unsigned calculation. This is the name, logical instruction, arithmetic instruction, negative, no meaning. Bit 31 of the result is set, indicate a negative number in signed operation. All 0 carry and overflow also in the same process. This is the code I pasted from the file. Question number 7, find what types of control logic unit used for and correlated its performance with the type of control unit in a module 3 in computer organization and architecture syllabus. The ARM microcontroller stands for Advanced Risk Machine, ARM. It is one of the extensive and the most licensed processor cores in the world. The first ARM processor was developed in the year of 1978 by Cambridge University, and the first ARM RISC processor was produced by the Acorn Group of Computers in the year of 1985. These processors are specifically used for portable devices like digital cameras, mobile phones, home networking modules, wireless communication technologies, and other embedded systems due to the benefits such as low power consumption, reasonable performance, and extra. This is the diagram architecture. Control unit 8051. This is also the diagram CMOS 5-bit microcontrollers. Question number 8, explain the memory management system and the processing elements selected. List addressing capabilities. Memory mapping technique followed. Find advantage of memory design management techniques over the concept given in module 4 of computer organization and architecture syllabus. The MMU contains the following: the table walk unit, which contains logic that reads the translation table from memory. Translation look aside buffers. All memory addresses that are used by software are virtual. These memory addresses are passed to the MMU, which checks the TLV for recently used cached translation. 8051 memory organization. 8051 is microcontroller memory. It is divided into program memory and data memory. Program memory ROM is used for permanent saving, while data memory is RAM. It is used for temporary storing and keep immediate result in a variable. Internal data memory up to 256 bytes of internal data memory are available depending on the 8051 derivative. External data memory access to external data memory is lower than the access to internal data memory. There may be up to 64 KB bytes of external data memory. Several 8051 devices provide on a chip XRM space that is accessed with the same instructions as the additional external data space. This XRM space is typically enabled via proper setting. And question number 9, elaborate the pipeline and the parallel processing capabilities of the unit and hazard management technique. This also explained as follows. Instruction pipeline is a technique for implementing instruction level parallelism with a single processor. Pipeline attempted to keep every part of the processor busy with some instructions by dividing incoming instructions into a series of sequential steps. Uh, EIF fetches the instruction into an instruction register ID, instruction decode, decodes the instruction from the opcode. AG address generator generates the address. DF data fetch fetches the operand into the data register. EX execution executes the specified operation. WB write back the result to the register. This is the structure, the way they diagrammed. Fetch, decode, execution. Fetch, decode, execution. They are prerequisite like a sequential way. Pipeline hazardous, also explained like this. From reset to install register back by arrow. And this is the advantage of pipeline instruction throughout increasing the number of pipeline stages. Disadvantage is also explained in this way. Designing of the pipeline processor is complex. Instruction latency increases in pipeline processor. The throughout pipeline processor is difficult to predict. And not only the least, question number 10, the last one, find whether the processor level parallelism is available in the element selected. Illustrate cache coherence protocol used for handling memory hit or miss. This is the diagram for this question. Cache coherency is an important concept to understand when sharing data. There are three mechanisms to maintain coherency. Disable caching in the simplest mechanism, but may cost significant CPU performance. And the third one is software managed coherency, hardware managed coherency, cache cleaning or flashing if any data is stored in cache is modified, and also cache invalidation if the process has a local copy of data but external agent updates, and this processor and the memory attached together. Separate data and instruction cache, unified instruction data cache. This all about digital assignment 1. And before I go to digital assignment 2, I will show you which online tools I used for this diagram. All the diagram I used for this online tools is not this one. I used this flowchart maker online diagram software, and I kept it in a bookmarker on the top of the Chrome to use easily whenever I want. If my PC also is switched off, when I am switched on and I want to use, I will click on here to make a Google Drive. I clicked here. Okay. This is the way how I opened and make it to drive. This is the online tool I used. Everything here I want is here. Diamond, circle, square, rectangular, arrow, and direction. Everything here. I use this online tool to draw all that, and I'm going to create digital assignment 2 now. Digital assignment is this one. This is my PDF. I uploaded it on Vito. Analysis of a floating point unit from open access journal using the concept learning the syllabus. I chose this paper, IEEE. Uh, the topic of this paper is out of order floating point coprocessor for risk DICA. Question number 1: explain how the selected paper related to the COA syllabus or curriculum. It's explained. I think I explained it briefly here. Everything is written down as follows. The floating point operation are important and essential part of many scientific and engineering applications. Floating point coprocessor, or we can say shortly FPU, performance operations like addition, subtraction, division, square root, multiplication, fuse to multiply, and accumulate and compare. Floating point operations are a part of ARM also, which I used previous for digital assignment 1. ARM Cortex M1, and this also ARM MIPS and RISC-V instruction set. The FPU can be part of hardware or implemented in the software also. This paper detailed an architectural exploration for floating point coprocessor enabled with RISC-V floating point instruction also. And like this, question number 2: draw the existing architectures discussed in the paper using appropriate raster graphics editor software in encapsulated PostScript file format. Uh, this is the diagram I did recently because you said to change the diagram by bold line. So this is the diagram I updated by bold line, except the text word, everything is bold like this. All diagram and this the repeat the previous diagram before the updated. This also previous diagram before updating happen. Question number 3: tabulate, draw the tabulated result. I also draw the like this. This is the tabulation. Question number 4: also propose the architecture discussed in the paper using diagramming, vector graphics, application software in the same way, encapsulated PostScript EPS file format. I did in the same way. And question number 5 also ask draw the transistor level internal diagram using electronic schematic capture. I did like the so. Question number 6 also compare the proposed architecture with existing architecture in your reference book. Everything is the same way. Question number 7: list the advantage of proposed design over the existing design. The advantage: output decoder logic only commits oldest instruction from pipeline. This ensures in order to commit checks, it checks token from instruction scheduler key and fetches oldest token and commits instruction only if that taken match with the completed instruction. And I think it's explained. Question number 8 also lists the merit and the demerit or advantage or the disadvantages proposed and existing techniques. Merits are intact FPU, others have very low power consumption. In exact FPP, others require small area. In exact chips are smaller. In exact FPP, others can nearly 15 times more efficient in terms of speed, area, energy as compared to existing architecture. So then I wrote so many merits. So these are the merits used for this one, and demerit is also there. But demerit is so few I wrote because demerit is on many few. Uh, this was the idea, so it's difficult to exactly replicate the equivalent hardware design. These are the disadvantages. It's inexact circuit error margin can be significantly large times, which would be could it give wrong processed values and the result. Question number 9: list the application purpose. This is the application purpose. Uh, the last one, draw the flow chart. This is the flow chart drawn for that. And this is the reference where a paper or a IEEE journal I used. This is different. Last one is reference line. So digital assignment also done like this. Diagram for this also I used it as I showed previous. The same flow chart on the design maker online tools. I draw by using that one. This is why what the digital DA1 and DA2 looks like. And thanks for watching.